Great to be here, especially after the pandemic, when we're doing Zoom sessions and finally face-to-face. I love all the presentations going bottom up to oscillators, and I have to let you in a little secret. I am a distinguished engineer. I've been a distinguished engineer for 4 companies, yet I don't know how to design an oscillator. And I'll tell you why. I went to the same undergraduate school as a lad, and they told me, I'm going to teach you how to build an amplifier, and I'm sure you'll get it wrong, and you'll get an oscillator. So I don't need to teach you how to build an oscillator. I'm sure that Elad doesn't, probably Gilad doesn't know how to build an oscillator. So today's session was great. So I'm here to put it all together. I've been away working remote from 3 continents for more than 2 years. And while that happened, Elad and Ahmad and a few other people did a great job of pushing this all the way to the state it is. So I think it's time to bring it back and put it all together at the big picture level. For this presentation, I got some help from many different people. Yeah. So I got some help for the different parts of the stack from Eric, from Broadcom, for issues that have to do with the NIC. From Ahmad, of course, for the use cases, for the operator. Lasse for the stack, and Scala for the simulation part. It's like going back in time in the sense that we had some ideas early on. I spent like 4 years at Facebook. It was called Facebook then, not Meta. And that's going back in time and putting together the old ideas. It's like going back in time also because when I joined Facebook, the stock was at 128, and it's at 130 now. So it's more or less the same valuation, but you could do worse. You could have bought kind of Argentinian bonds. Don't laugh, I did. Anyway, so what I wanted to capture here is the value of simulating data centers. When we put it all together, I had 2 choices. I build a 40 megawatt data center. It will take it 2 years and a ton of money just to prove that PTP will work at scale. Or I can run a simulation, where the simulation runs at AWS. They already built that data center for me, and it can simulate an entire 200,000 server data center. So it's the value of simulations. So we started discussing that. We presented twice at OCP. The first time, whenever you say simulations, people beat you up with how do you know that your model matches real life? They ignore the fact that since 1963, we no longer blow up nuclear bombs. We simulate them because there is a partial ban on that. So that's what led to HPC pretty much computing. So we can simulate nuclear explosions instead of making them happen. Or that we have weather prediction. I can look on the, on the web and see what the weather is going to be tomorrow. All that stuff is a simulation. So we do the same thing. I was talking to somebody from Meta today and saying our company actually started with weather prediction. And paradoxically, simulating a data center network is like weather prediction. It's very, very close to that. So we gave a talk where we joined forces with Keysight. Keysight, the makers of instrumentation and the Ixia boxes and so on. So when people beat me up and said, how does it know that it matches real life? We invited Ixia as a partner, and they took our topology, our workloads, and they measured that in a physical setup, and we correlated the results to within 1%, including TCP stacks and everything else. Took us like half a year of work, but once it's correlated, people have the confidence that our work makes sense. We presented that in July to OCP, a very good presentation to the networking group by people that have no accent, so it's much more pleasant to listen to them. Feel free to click there and figure out what we've done there. I came back late July to make a proposal to OCP TAP, and essentially said, here's what I can do for you. And I went very wide but very shallow on all the things that we can do. From guidance from you, and specifically from Ahmad, we picked a couple of things so we can go deeper and go do them. So that's the reason we are back here, to really get going. The company itself, Scala Computing, is a vertical SaaS company. So we run simulations, we run them in the cloud. We essentially do model development if we have to. The customer can do model development. But at the end of the day, we essentially run compute cycles at AWS for a particular vertical. And you get to have your results without having to deploy any infrastructure. If you have a laptop and a browser, that's all it takes. I think that this is valuable, like in Latin, you say, "Chi bono," who benefits from that. There are 2 types of companies who benefit from that. If you're an operator, we have models for real devices you can buy. So you can do what if. I'm about to make a decision on deploying an application or designing a data center. I can do a what if and have real devices that I can model and make decisions. If I'm a semiconductor vendor, I also benefit because now I have workloads from the operators, so I can do my next generation that matches the needs of my customer. So that's a typical, we're a funny company, we're very small, about 30 people, but all our customers are huge, are tier 1 companies, very, very anomalous. I started my career as a design verification engineer at Intel, so I always loved simulations, but I hated building the simulator. So at Scala, I solved that part. I can go straight to the experiment, use the GUI, and not have to code at all. I have a son that was addicted to a game called Roller Coaster Tycoon, and you simulate essentially an amusement park. And the insights that you get into that type of activity is much deeper than going to Great America. By the time he was going to Great America, he knew more than me. He said, oh, this is a chain up built by Switzerland. Like, do the experiments like what happens if the loop is a full circle, people start throwing up because they get dizzy, and then you get less of them so you have global visibility. You feel like I'm God, I'm running this data center. So I'm not into games, so I'm doing the same for data centers instead of amusement parks. So that's the history of simulations. We are at OCP, so we have to use the letter O about openness. We want to be as open as a real data center is, which is whenever there is an Ethernet link, which really means IP over Ethernet, you have the expectation that the far side of the link is interoperable, even if it doesn't come from the same vendor. When you create a simulation model, all companies have simulation teams that run simulations. They are all in-house, monolithic, and not transparent. There was a talk 2 days ago by Cisco showing an ML training. It was done in-house. You have no idea what is simulated. I went to the guy. I said, what's the transport layer? Oh, no transport. What do you mean? You do ML without the transport? And they present data, and it's not transparent. You cannot have accountability if whoever is doing the simulation is the same person that's going to sell you a device. So what we're saying is we created a consortium. We said, bring your model. You can code it. We can code it for you. But it can operate. We can assemble at runtime components in binary from different vendors, and they operate in the places that you expect. Whenever you have an IP or Ethernet link, you can connect devices. Whenever you have a PCIe link, you can connect devices. Whenever you do a write to a sockets interface, that's the interoperability. So it's modular, and it's completely governed by a consortium that is standalone. In the future, if we go big, we'll be happy to bring it to OCP and attach ourselves to OCP or to a Linux Foundation or what have you. But it's the only simulation that is open, transparent, and consortium-based. So here I'm showing where the interface locations are. There are 4 types of models in our simulation. The switch routers, which you see in blue. Here I show a 2-stage clause for simplicity, but usually the data center is more stages. So the links are the interoperability interfaces, and the consortium define the data and the metadata that moves over the interfaces, just like you have REST APIs or stuff like that in a real data center. The interface between the switch and the NIC, again, is an Ethernet, IP over Ethernet. Above that, you have the network stack to network interface within a host, and then the application to a network stack. So let me double click into an endpoint, because that's where I connect this to PTP. So here on the right, you see the physical representation. You have the root complex, and you have the processor with the DRAM. Below, you have the endpoint, which is the NIC, with a PHC, with timestamping. That maps to the simulation model, where you have an application writing for data movement, as you see blue to blue, into a network stack, right? And that is typically a send-receive, or it's a read or write into a socket type of interface. But it's a well-defined standard interface, crossing maybe the boundary between user space and kernel. Below the stack into the network interface, you have the enqueue the queue into some NIC device, like a descriptor ring or something like that. That's what we model over there. And we have ioctals. In the case of the yellow stack, we have a new stack over here, which is the PTP stack. You also have the ioctals to access the timestamp and the PHC. So that's the scope of the simulation that we have in mind, so we can do PTP. We like this a lot because most of the applications we've done move data, so your results depend on the assumptions you made about the application. So now they don't bid me over fidelity of the stack, but they tell me, how do you know that the application represents a real-life application? So that's always an interesting conversation. For PTP, I don't have it, because PTP is a service, not an application that moves data. So I can say, okay, let me show you that I have 1 microsecond accuracy across the data center and have all the metrics and be done with it. So this is what we're planning to do. The guidance we got for the goals out of the many things we presented is, why don't you look at the interactions between PTP and BGP at scale? Now it has done that, it's very hard to do that at scale. PTP is the only application that the traffic is not leaf, spine, leaf. So you have no path diversity because you inject the traffic from the spines. So BGP may not help you because you may not have route diversity when you lose a route. And that's why we love working with TimeBit, because If that doesn't work, we're going to look at client-side failover if there is no path diversity, right? We think that that could be a very compelling thing. What happens if you do have path diversity and now you have oscillations because BGP kicks in while your BMCA is kicking in, and before you know, you have oscillations and stuff like that. So these are some of the questions we're going to tackle. We're going to pretend that we have a real data center running BGP and prove at scale that PTP holds water, that everything works at scale. And here are some of the examples of the questions I have in mind. In my experience, when you sit down and start writing a simulation, that's when you start really asking yourself the serious questions, and new questions will come up. The second thing is that we want to do is to validate the stack at scale. That includes the filter, the servo, or whatever goodies, innovations we want to postulate for the endpoint. So what we want to do is actually create an environment where the yellow box I showed you can be the time bit stack, for example. So we can do a PTP4L, we can replace it with time bit, so we can prove to Ahmad, to whoever wants to deploy, if we want to deploy, convince Amazon, like Anand was saying, we can say, hey, here's a model at scale, and turning on PTP, it's not that hard because maybe the devices you have in the network already support transparent clock. So all you need to do is make an SDK call to put it into transparent clock, everything else is software. So the question that I got, I think it's easier than it appears. And we can say, here's the solution, PTP is a no-brainer. So what we're planning is to collaborate so we have a real production supported stack in addition to PTP4L and do all the what ifs on that. As I mentioned before, I like DC PTP simulations because it's very likely that we're the victim traffic. We want to be the one that gets affected by ML training, by bursty kind of NVMe traffic or something like that. The PTP has a very interesting ratio of message raised to precision. Whenever I was doing NVMe type of simulations, you get into the microsecond type of precisions, but at throughputs that are 100 gig. The rates are incredibly high. Here, the message rate is relatively small, which means that the incidence of the fact that I'm not running the real protocol stack, but actually an embedded version within my simulator is less material because the compute element of my simulation is going to be more accurate. And I talked about the fact that the topology is going to be just spine to leaf, which is a different thing. The other reason that we think that this is high impact is what happens when things go wrong. And we have many internal discussions when I was back at Facebook. Whenever I have data loss, nothing bad happens. There is a throughput problem, then everything takes a little bit longer. Whenever I have the wrong notion of time or time goes backward, I have data corruption. Bad things can really happen. So whenever people say, hey, show me your P99.9 for your SLA, okay, if I violate the SLA, I give some money back for my customer. If I have the wrong notion of time, it's not clear at all that a 3.9 availability or metric is sufficient. I think that people will want 5 nines or even higher than that. And the only way of proving that is via simulation. It's just too expensive to build a pilot at scale. So here's a vignette I have from another workload that we just presented. There was a presentation yesterday by Golan from Broadcom, where people were trying to answer a question that nobody had the answer for this. What is better, a cell-based switch with VOQ or a packet switch? I was at Broadcom, my customers used to ask, hey, you're selling the Cadillac, you're selling the Fiat, which one should I buy? And I'll start hand-waving and say, it depends, I don't know what you need. So finally, we put the simulation models. We have simulation models now for the Ferrari, for the Fiat, and we run an ML workload, and we have the answers for that. So we can quantify the answers for that. So Golan presented exactly this slide, which is what is the job completion time for an all-to-all kind of collective for ML for devices that do not yet exist, for the Jericho 3, Ramon 3 devices that are about to ship. And all that was done using our platform, real devices that you will be able to buy. So this proves that our platform is real, that we can work with real devices and present data for the most demanding applications in the world. If you think about the ML, whenever I was doing simulations, I always simulate bursty on off. Why? Because it stresses the system like heck, and I change my duty cycles to 50-50, 70-30, and so on. And people say, well, what about Gaussian? What about the arrivals are really random? So I say, okay, fine, let me do the superposition of many bursty on-offs with random phase, and you get Gaussian. So I get to stress the system with one that I can understand, and then I have the central theorem, and I have the Gaussian. When you think about ML, it's not bursty on off. It's 100%. ML is like you want to go to somewhere, but everybody wants to go everywhere, all of them at the same time at 100% duty cycle. There is no harder workload than ML training. And that's exactly what we simulated using the platform. Call to action. If I summarize this, is guide us, join us. We need help. I mean, we have one of each to guide us, but I love, for instance, to work with Kevin and Intel. At the moment, we have a root complex model that models the latency of a DMA read, of a PIO write, all that stuff. I love to extend it one more hop and capture that 500 nanosecond and the jitter and all that stuff to enhance my model. Love to work with Elad and Mellanox and say, oh, we have multi-host NICs, you have a single PHC for the four of them. Let's go model that stuff so we can jointly go to the operators that we have not gone, not the people like Ahmad, the ones that are not sold, like Anand was saying, and say, this solution is ready to go. And if you want to approve, just use our URL, have a browser, and run the simulation in your laptop.
Thank you very much. Any question? Please.
Sorry, time again. But great talk, I appreciate it.
Thank you.
But you mentioned of the two PTPs at PTP4L and some others. Now, how do you handle like proprietary implementations of PTP, which are commercial grade? I mean, what kind of models? You would be interested in finding out how it would perform.
Proprietary for the Grandmaster, for the stack, or for what?
For across the board, for both Grandmaster and for the boundary clocks and stuff in the data centers.
So at the moment, the simulation we have in mind is the one that has no boundary clocks. It's transparent clock throughout, because that's the guidance that we've been given for what's interesting to deploy. We could implement a boundary clock if somebody wants us to do that, or they can develop it on their own and do the comparison of what's a jitter propagation of one versus the other.
Yeah, because of the proprietary nature of our stack and servo, I think we were just wondering what kind of interface or model we should be.
Okay, so I've been a little bit negligent on telling about the engine. So the simulation is distributed NS3 running over MPI at AWS. NS3 is an open source simulator, and it has a technology called DCE, direct code execution. So if you like to integrate a stack that runs in a server, you could do that. Enable DCE and actually invoke your proprietary code without telling us anything. The other thing that we do within the consortium is you can implement your workload as a shared object file, upload it to a platform in binary, and share it with other people without disclosing your implementation. Like when we talk about openness at OCP, we're kind of lying. We want everything to be open, but semiconductor vendors will never open the RTL. The open is in the software, maybe the firmware, and the board level design. Silicon is meant to be proprietary because you do a tape out that costs you $20 to $50 million. The last thing you want to do is say, okay, open Kimono, copy me, right? So when you talk about openness at OCP, it's about openness of the interfaces between the components that are proprietary. The simulation is exactly like that. You don't have to disclose your simulation model. You interoperate at the interface.
That's right. So I just wanted to understand if you have a very well-defined interface.
That's right, we do. We do, and it's codified by the consortium.
Gotcha.
And we have a model for sharing that interfaces where essentially we come on the platform, your admin will communicate with the admin of whoever model you want to use and say, hey, are you willing to share that model with me? Right. And the guy will say, oh, friend or foe? Yeah, I'm sharing with you, I'm not sharing with you.
Gotcha. Thank you.
Any other questions? Thanks again.
Thank you.